Hello everyone. Today I wanted to prove this theorem in real analysis, which is that a sequence of real numbers is Cauchy if it's convergent. So that means convergence implies that the sequence is Cauchy. So before we get started, I want to go over the definition first. A sequence is convergent if there exists x. So this is the limit. If there is an x such that for all epsilon there exists n such that every term that comes after that, the difference between that and x is less than epsilon, meaning that the sequence is getting closer and closer to the limit, which is very, I think, intuitive. The definition for Cauchy is a little bit tricky. So it looks a little bit similar, but given an epsilon, there exists a number such that every term that comes after that, if you take two terms after that, the difference between them will be less than epsilon, meaning that two terms are getting closer and closer to each other. So they're kind of similar, but a little bit different. And in real numbers, we can show that convergence implies that the sequence is Cauchy. So let's prove this. So suppose that xn is convergent. Is convergent. Then let x be the limit. We can assume that the limit exists because we're assuming that the sequence is convergent. Now what we want to do is to show that xn is a Cauchy sequence. And to show that this is Cauchy, we can just follow the definition. So first let epsilon be given. So the epsilon is coming from here. We're just going to follow this definition. Then we need to find some n that has this special property. For that, we're going to use the fact that xn is a convergent sequence. So we're going to use this part of the definition. So for any epsilon, there exists an n such that every term after that. So let n and not be chosen such that for all n after n naught, x minus xn is less than epsilon over 2. So it might seem a little weird that we have epsilon over 2 here and then epsilon over here. But this is okay because epsilon was any number, any non-negative number, any positive number. And then epsilon is a positive number. So if you divide it by 2, you still get some positive real number. So this is okay. Then now, going back to the definition for Cauchy, we can just use the n naught for this. Then we are going to have for all n m that are larger than n naught, xn minus xm equals xn minus x plus x minus xm. Note that here we're just adding x and then subtracting x. And this is less than or equal x minus xm. And this is by the triangle inequality. And then this part, it's because of this. We assume that we picked n naught, so that everything that comes after that, the difference between that and x is only epsilon over 2. So now we show that for all epsilon, there exists an n, there exists an n, such that an m after that, bigger than that, the difference between those two are less than epsilon, and then the difference between these two are really just less than epsilon. So yeah, we just proved that xn is Cauchy if it's convergent. Thanks for watching.